Hello everyone, today I'm going to talk about the visual learning framework to tackle unsupervised hierarchical semantic segmentation. Semantic segmentation is a task to put pixels into semantic categories. Given an image, we would like to know if an image pixel belongs to the person, bike, or cow category. However, naming the semantic categories is impossible without supervisions from labels. Unsupervised semantic segmentation is in fact a task of grouping, not classifying pixels from unlabeled images. There are two major approaches to infer labels from pixel groupings. One is to cluster all pixels into fewer groups, and each group denotes one category. Another is to predict pixel labels by looking up neighbor's major category, where a label set is given during inference. We follow the retrieval approach and consider it as a feature learning problem. We learn to generate pixel features from unlabeled images and use the features to conduct nearest neighbor retrievals on image segments. There are two ideas to learn visual features from unlabeled images. The first is to discriminate between image instances. The idea is that features should be invariant to visual changes, but discriminative between instances. The second is to develop pixel features based on visual appearance. Pixel features should be coherent within visually similar regions, but distinguished from dissimilar regions. These two methods contrast features at a single level, either among images or regions. However, semantics have multiple levels of granularity. For example, the left image can be parsed into coarse categories such as person, rock, and road. The image can also be parsed into fine categories such as human body parts. The question is, which level should the segmentation method target at? Most existing methods either ignore such ambiguity or just presume a single level of granularity. Instead, we embrace the ambiguity of granularity. We exploit the hierarchical structures to develop our feature representations. Our intuition is twofold. First, we see the baby has a face and body. This introduces the idea of hierarchical grouping. We want to learn a good feature which reveals consistent groupings across scales. Secondly, babies have the same semantics, though appear differently. This introduces the idea of multiview cosegmentation. We want to learn an invariant feature for the same region, regardless of appearance change. We obtain cosegmentation in two ways. One is to match coherent regions across views. We segment the original image into coherent regions from edges and match regions in other views. Such groupings help us to ground features by visual appearance and correspondence. Another is to co-cluster segments among different views at multiple scales. We regularize our feature based on such fine and coarse grouping cues. We can generate features and cluster them at each level of granularity. However, it does not guarantee the consistency of hierarchy. We desire a consistent multi-scale grouping such that the segments of a fine-grained cluster should belong to the same coarse grain cluster. Our idea is to predict the fine to coarse transition probability, with which finer clusters are merged into coarser clusters. The transition probability is predicted by cluster features. We conduct multi-scale grouping with a clustering transformer. It takes current level cluster features as inputs to output the transition probability and next level cluster features. By stacking several clustering transformers, we derive a consistent hierarchical grouping of an input image. Here is an overview of our framework. Given an image and its augmented view, we generate pixel-wise features using a CNN and partition images into segments. We conduct multi-view cosegmentation using coherent region matching and multi-scale feature clustering. We impose pixel to segment contrastive losses based on each cosegmentation. The coherent region grouping helps our model to ground features with regard to visual appearance and enforce correspondence across views. The multi-scale grouping regularizes features by hierarchical consistency. And lastly, we impose the goodness of grouping to optimize our clustering transformer to seek balanced, compact, and distinctive clusterings. We compare our hierarchical segmentation results on VOC. Our segmentations capture semantics at different levels of granularity better. We compare our unsupervised semantic segmentation on object and scene-centric datasets. Our results outperform other image-to-image contrastive learning frameworks. Notably, these baselines do not work on cityscapes and kitty-step datasets, where most images contain similar street scenes covering almost all categories. Lastly, we conduct contextual retrievals across granularity levels. We're able to retrieve the same granularity segments as the queries. Thank you for your listening. You're welcome to try our code at GitHub.